What? Yes, and that's probably, yeah, because she always shows up for class, so yeah. Okay, so nothing's due. Class is going to meet. There's no lab tomorrow, so I'm going to go hiking. I did manage to get an exam together. That was somebody, Sigly. And I will work on the key for it and fine-tuning it and making sure that it's not ridiculous tomorrow after I get back from my hike. So I'm just going to stay at home. I did not get spring. This is the second year in a row I haven't gotten spring break. Sometimes that's like the only vacation I have because I work all summer. If you can call that work. I am employed all summer. Some days it's slow. Some days I work a lot. Exam 2 is going to be next week. If you want to do the remote exam, please send me an email and we'll set up a time that's convenient for both. Try to get some time that's convenient for both of us. I will suggest a time to try to get everybody to take it at the same time if I can. The day after, then we're going to continue Lab 4. The class meeting after the exam, Dr. Cambeau is going to come in and talk about what Samsung and TSMC are doing to get down to that 3 nanometer node and beyond. And then we'll start with frequency response and Bode plots and things like that. Yay, more Bode plots. They're a lot easier than they were in 280. Everything's easier than it was in 280. Okay, so we talked about the Accelerated Masters program. All the stuff's posted to BB Learn already. You will get 2 sheets of notes for the exam. We talked about the FENFETs. Dr. Cambeau will talk a little bit more about this. The nanowires have gone away and become nano sheets. They're just a little wider because it works better. And that is what Samsung's doing at the 3 nanometer node, last I heard. Okay, we want to talk about common mode gain and differential mode gain. And this is typically what the common mode voltage looks like. There's usually some kind of DC component to it, and there's some kind of pseudo-random AC component to it. It's actually the sum of 2 things. But pretty much when we analyze these circuits, we're going to say, we're going to treat the common mode voltage like it's a DC voltage. And the common mode will be the DC input. So when I draw the DC circuits, I'm going to use the common mode voltage. The differential mode is our signal voltage, and that will be included in the AC circuits. That will help make things a little bit more sensical. Now, if I can, yeah. I'm trying to remember where this was going. Let me look at the next slide just to figure out where this is going. Okay, this is going into common mode rejection ratio. So if I want to draw the small signal circuit of this, I would have be in common mode, would be part of it. The small signal version of this, I ground my DC sources. My DC current source goes away, becomes an open circuit. If I can make that RSS go away, then I would have absolutely no common mode gain, which would be a good thing. The common mode rejection ratio, it's defined as the differential mode gain over the common mode gain. That's probably the most important piece of this whole piece of the lecture that you can get out. Usually you look it up, unless you're the design op-amp designer, you look it up on the data sheet. It's got some weird frequency dependence here that we will get to after the exam. But for now, it's just a constant differential mode gain over common mode gain. Really typical values you see, most op amps, this comes out to be 100 dB. If you're looking for something that is really good, you can find it up to 120 dB. Calculating it, it's pretty straightforward, 100 over, and it's the magnitude, so 3 2 zeros and a 1, 20 times the log of that. That is 1, 2, 3, 4, 80 dB. Four zeros. And you want it to be fairly large. Not a great amplifier, but okay. Now, if I look at this, the equation for the common mode gain, if I have my output voltage at 1 over Vn common mode, it's just the gain of that transistor. And the calculation comes out to be, it's RD over 2 RSS with a negative sign. There's also some common mode gain in the other side of the diff amp. Now, if I take the differential output right here, I take my differential output is the difference between VO2 and VO1. I get negative RD over 2 RSS minus a negative RDD over 2 RSS, and that comes out to be 0. I have no common mode gain as long as I can perfectly match the RDs to each other, and I can perfectly match the transistors to each other, and I can perfectly match the trace lines between them that are connecting them together, lay the whole circuit out identically, just copy it over. I can pretty much get a perfect common mode rejection ratio. That never happens. The way people fight this and get the common mode rejection ratio higher is by getting the matching on the transistors better across the process. And so if you use larger transistors in a smaller process, like you use 100 nanometer transistors in a 5 nanometer process, you can make the 100 nanometers pretty exact within like 0.0 several, less of a percentage. So the big mismatches we can see on here are RD and GM, the gains of the transistors. We'll look at those, and it pretty much turns out any kind of mismatch is going to have the same effect on the common mode rejection. So I go through here, I've got one resistor that's RD, and this one's a little bit bigger. It's RD plus delta RD. So this is the gain, the common mode gain on side 1. The common mode gain on side 2, I'd have to put in that larger resistance value there. When I subtract the two of them from each other, the algebra comes out. My common mode gain is just, it's no longer 0, it's delta RD over 2 RSS. And in order to make this simpler to calculate, what I do is I both multiply this, I multiply by RD over RD. So I end up with RD over 2 RSS and delta RD over RD. This is the percent of mismatch, pretty much. If it's 1%, I put in 0.01. So figuring out the tolerances on your components, you can figure out what the common mode gain is going to be. I can make the common mode gain smaller by matching my components better. And when I do CMRR, it's just basically AD over this common mode gain. It's coming out to be 2 GMRSS over the mismatch percentage. So again, the only thing I can do here is match my components better.
And you were saying the way to do that was to use like smaller.
Yeah, if you have a process that you can build features down to maybe like a couple of nanometers. One trick you could do is, so you've got precision down to a couple of nanometers. You probably have, okay, let's just make numbers up here. You've got a 1 nanometer process. That means your precision is probably good to about at least maybe 1% of a nanometer or 10% of a nanometer. Okay, so then if I build a 100 nanometer transistor in that, my precision on that process is still 1/10 of a nanometer. And so I can match things a little bit easier there. I go to bigger devices. Yeah, they usually don't push the size. On analog circuits, they're not pushing the size limit because you might have several hundred transistors in an analog integrated circuit like an op-amp. So you're not worried about the size of the components as much. And so a lot of times they're doing things in like a 0.18 micrometer process because it's cheaper. But then the transistors themselves may be tens of micrometers. W over L may be huge. So yeah, so it's not like 1 nanometer to 100 nanometers. It's probably more like 100 nanometers to a micrometer is where they're shifting it between. Now that's for RD. Now we could plug some numbers in here. So I've got an expression for the common mode rejection ratio. What are RD1? RD1 would be 8K ohms. RD1. RD2, let's say it went plus 1%, so it would be 8K plus 0.01 times 8K, 1.01 times 8K, so this is 880 ohms. This would be 8.08 K ohms, would be my other resistor, RD2. If I wanted to find the differential gain, that would be GM big RO, GM AD, GM big RO. What do we use for our RO? Oh, it's going to be a little less than 8K. What did I use in the calculations? RD1, RD2. What?
Like 7.5K or something like that?
That
was weird. You didn't really write down your process.
Oh, with a 1% mismatch?
Yeah.
What I did is I wrote, okay, so if it's 1% higher, then that would be the 8K plus 1% of 8K. And then I just kind of like did that in my head. So that is 1% of 8K would be 80 ohms. And then I added that to 80K or 8K. The common mode, I'm not going to calculate that here. Okay, okay. The common mode rejection ratio, we've got a formula for a common mode. We've got a formula for AD. And we've got the formula for the common mode rejection ratio already. It is 2 GM, so 2 times 1,000 micro. RSS is 100K. And over delta RD over RD is going to be, in this case, it's going to be 2% because it's plus or minus 1%. So I could have a 2% difference in there. So this would be 0.02. and we can get the common mode rejection ratio is 8,000 times 10 to the minus 6th volts per volt. And then when we convert that into dB, it's just 20 times the log of CMRR. And that comes out to be about 80 dB. Wait, that doesn't seem right.
For your common mode rejection ratio, before we were doing the decimal conversion.
Yeah.
Why in the numerator do we get 2 times 1,000 times 100K? Because differential gain is just 1,000 times 100K, right?
Yeah, but it's like when you take the differential gain and you divide it by the common mode gain,
Oh, right,
that's where the 2 comes from. And it's the magnitude, so the negative sign goes away.
Actually, I don't think it'd be 8,000. I think it'd be like 1,000, wouldn't it?
2.
Because yeah.
I know. I'm having like I'm having mental issues with the calculation because it just is coming out wrong in my head, and I
think it's because you're using micro. I would just convert that to milli, because then milliamps.
Yeah, it would be milli. Okay, so 2.
Yeah, it'd just be 1 milliamp.
Okay.
1K.
Okay, so I really I doubt my calculation here. I just copied that down from my thingy. But 20 times the log of that would give you the CMRR. That's coming out to be 80 dB, which I don't. Oh,
also in the denominator.
I know where I copied down the wrong number. It's 10 kilo. It's 10 kilo. This is wrong.
Mm.
I can use my finger. This is, use this. The actual value is, it's 10 kV per volt, which comes out to be 80 dB. Yeah, okay. I can't write right now. I'm not frozen, but I am. I don't think I'm frozen. You know, that's a good question. Am I frozen? No, I'm not frozen. I'm just going into screen mode. When I change slides, it generally comes back, and I don't understand that. Okay.
Wait a minute, sorry. In the denominator of that middle equation, though, we have delta RD over RD. Isn't that 0.01 divided by 8?
When you say a resistor has a 1% tolerance, that is really plus or minus 1%. So if I picked, worst case, I could pick one RD out of the bin that was 8.08K, and I could pick another one that was 7.92K. So there's actually a 2% difference between those. So plus or minus 1% is a 2% difference range, and that's why I use the 0.02.
Okay, but don't we also divide that value by RD itself, in this case RD1?
Right, but it would be, yeah, it would be, if you did that, you would take, let's see, 160 ohms divided by 8K ohms, and it would come out to be 0.02%. So I just went for the tolerance and said, because delta RD over RD, delta RD over RD is going to be the 2%. That's why we kind of change this equation to make it look like that, because then I don't have to calculate 80 ohms for every different value, calculate what the 1% value is.
So essentially, instead of just taking the percentage value,
right,
you just take the actual resistance change.
Right. Yeah. So that's not really going to change. If I put a 10K ohm resistor there, it's not going to help me as long as it's a 1% resistor. You can buy 0.01% precision resistors, but you'll pay like 10 cents for them. They're horribly expensive. Oh, okay. So that is what happens if I do an RD mismatch. And I kind of saved this one and just copied it over here. I did that this morning. If I do a GM mismatch, the common mode, and I go through all the algebra and everything, the common mode rejection ratio looks pretty much the same. The only thing that changes is now I have the GM mismatch over the bottom, on the bottom, instead of the RD mismatch. So it doesn't matter which component is mismatched, it matters which one is mismatched the worst. and which value is mismatched the worst.
So if they're both mismatched, we just take whatever one is mismatched?
Yeah, it's the tolerance on the sloppiest device that you care about.
Mhm.
So that would be if you're trying to fix a common mode rejection ratio problem, you find the worst one and you fix that, and then you start finding the others. They start showing up in your equation, and then you have to go. Then suddenly you have 10 things you have to fix to go to another level of precision. Okay. So this is the differential pair with an active load. We're not going to go through the common mode rejection ratio for that. It is in the textbook. I did find it for Chris, the exact page. But it's going to turn out, we're going to do the analysis on this. We're going to get a much better gain because now instead of having the RD up here, we have the higher value of RO. So let's go through this piece by piece. This isn't as bad as you think by looking at the number of slides. We want to draw the DC bias current. Now this gate voltage has two parts for it. When we talk about DC, we're going to make this, remember, this is the DC part is V common mode. The AC signal part is the differential mode. So for the DC circuit, I'm just going to put V common mode here on both of these and deactivate the AC part of the circuit. My signal sources stay in. My I is 200 microamps. Now, since this is the DC part of the circuit, I have the same voltage on both sides, VG1 and VG2. All I have is the common mode voltage. The current's going to split perfectly. It will not split perfectly in AC mode, but it will split perfectly in DC mode. So we got all the drain currents there. How do V out and VD1 compare? They should be the same. V out should equal VD1 because we have this perfectly matched circuit. We have the same current going through them, so we're going to have the same VGS. So I'm going to have the same voltage here at the drain. Okay. Did I get that right? I'm just, yeah. V out equals VD1 if the currents are balanced. I said that before and I could think clearly. It's easier for me to think when I'm not talking. Now for the common mode range, we want to figure out here what is the range of V common mode to keep all the transistors in saturation. We have to keep them all in saturation. Now we're going to look at M1 first. So we want to keep M1 in saturation. And I have to do this slowly or I'm going to screw it up. The voltage at the drain we have to concern ourselves with the drain voltage. We're going to figure out, first of all, start here with, why are we doing this with? This is, okay, because, so the drain voltage here is going to be the same as the gate voltage of M3. VD1 equals VG of transistor 3. And we know that the voltage between gate and source here, so this is the source, and that's the gate. The VGS of the PMOS transistor is negative 0.55. That's negative, which means this voltage here has got to be 1.8 is my drain voltage. 1.8 plus 0.55. This voltage here is 1.25 volts. Okay. In order to keep M1 in saturation, I need VD1 greater than or equal to VG1 minus VT. Okay, so I can solve that for VG what? VG1 has to be less than or equal to VD1 plus VT. Okay, we know what VD1 is. We know what VT is. VT is positive 0.4, VD1 is 0.125. So VG1 has to be less than or equal to 1.65 volts. So that gives us one limit on my common mode voltage, because VG1 is the common mode voltage. Okay, now to get to the other side, I just know this in advance. I need to, what's going to limit me on the other side is keeping M5 in saturation. So in order to do that, I need the voltage on the drain at 5 to be greater than the voltage at the gate of 5 minus VT. How did I get there? VD5. Oh, okay. Thank goodness. Thank goodness I drew a picture. I doodled on a schematic and I pointed it because I couldn't figure this out this morning either. This is minus 1.8 volts. The VGS of my PMOS, my NMOS transistors is 0.6. So this is negative 1.2. So the gate voltage on 5 is negative 1.2 minus 0.4. And so my VD5 has got to be greater than negative 1.6 volts. That's VD5. I'm going to draw that one in here. Negative 1.6. Now, to figure out how that relates to VG of 1, I know VD of 5 is also VS of 1, looking at the schematic. Okay, so the source voltage has got to be greater than negative 1.6. Now, to barely have this transistor on, I need at least a threshold drop across that gate. So my VG1 is going to have to be greater than, did I really do that? Oh, well, we have it, it's got to be greater than 1.6. I'm going to argue with myself on that. Greater than 0.6 minus 1.6. 0.6 minus 6. I'm going to argue with myself here and say that number to barely keep it on would be 0.4. To keep it on at this level and maintain linearity, it would be 0.6. So 0.6 minus 1.6 is negative 1. VG's has to be greater than negative 1, but I could have it at negative 1.2 if I just barely kept it on. Okay, So the range of my voltage on the gate is somewhere between 1.65 and negative 1.2-ish. 1.0, 1.2-ish. Depending upon if I want this really to be linear or to be starting to go into saturation.
So wait, is VG1 supposed to be equal to 0.6 minus 1.6 or 0.4 minus 1.6?
Yeah, that's what I'm arguing myself about. It would be 0.6 if I wanted to keep the 100 microamps flowing through it, and I wanted it to be linear. It would still be in saturation if I took it down between -1 and -1.2. But the gain would be starting to roll off because the current in that transistor would be starting to go down.
Because we're right down at the threshold level.
Yeah, you're getting really close to the point where it's just starting to turn off. You could technically get voltages down to -1.2 out of this, but it would be not very linear, and your gain, your circuit wouldn't be behaving properly.
And turning down the voltage would be nice because that'd be less power consumption, right?
Yeah, you'd have less current and you'd have less power consumption, but you'd lose the linearity of the circuit. So it wouldn't be, your circuit wouldn't be behaving well. I could put, my gain would be changing rapidly with voltage. Yeah. That's what that was the argument I was getting in with myself, because what I had written down wasn't really matching what I wanted to do. Or what I was thinking at the moment. We want to look at this and figure out the short circuit transconductance. And this is what I see going into this gain. Yeah, I don't like this. I know. I didn't like this morning either, but I kept it in. I didn't delete it. If I want to figure out what the equivalent circuit is of this, I just want to measure it. What I could do is go into the lab. I could short the output to ground. And I'm looking into this output node right now. This is what I would see. I short it to ground and I apply an input test voltage of VID. So I apply input voltage of VID, whatever that is, and I measure the output current. So I out, in this case, the current coming out this way, all the current would go through the short, none of it would go through R out, would be GM VID. So my GM of that, if I'm trying to measure GM for that transistor, it would be the output current divided by the input voltage that I put into it. Now I want to figure out what RO is. So I'm trying to use my test equipment, intelligently and figure out what all these values are. So when I'm measuring RO, I'm going to take this off and I'm going to replace on the output, I'm going to put a test voltage in a reasonable value that does not blow up my circuit. And now I can measure the current coming out of that I test. And my I test, I have no input in this case, so my VID is 0. So this current source is GM times 0. It's going to go open. My V test over I test is going to give me RO. This is called reverse engineering. Sometimes people do that. You buy an amplifier module from another company and you want to actually make measurements on that, figure out what the GM and RO that you actually have is, not what's in the data sheet, because for some reason you don't believe the data sheet, or you want to, because things aren't working quite right, you can perform these quick measurements and figure out what is the GM and what is the RO of that amplifier. Is one way of doing it. And yes, I've done that plenty of times. Sometimes what I found out was it wasn't the data sheet that was wrong. I had something hooked up wrong. But going through the exercise of doing this test helped me to find what I had hooked up wrong. Sometimes I just had a bad amplifier and I had to replace it. And occasionally it was a little out of spec. Okay, we want to look at this. This is the diode connected transistor. What is the small signal equivalent circuit? Well, small signal equivalent circuit always looks like this. We're going to put this in. I've got GM, VGS. I've got some RO, little RO. I've got some voltage here. This is my source, this is my gate, and this is my drain. So what have I done to this? I've connected the gate to the drain. There is my diode strap right there. That is how it's connected. So now, ooh, this is kind of interesting. Because this, remember the 1/GM that shows up in the whatchamacallit? And when we're looking into the source of the transistor, a lot of times you see a resistance of 1/GM. I'll kind of argue my way through this in a minute. So in this case, VGS is the voltage across that current source. So I've got VGS, the current I through that source equals its voltage times GM. The voltage across it times GM. This looks like, that's not a mo. V equals IR. It's acting like a resistor. And we can say 1/GM, V would equal I times 1/GM. Okay.
And in this case, the small signal is that little v, little g, little s, or big V, little g?
Yeah, this is it. I just said my little v, little g, little s would be my voltage here. But it's the same as the voltage that in this case, because I've done the diode connection, this voltage here is the same as this voltage here. And then I just kind of applied Ohm's law to that one. Okay. So we want to draw the small signal circuit. Oh, great. And we're, no. Okay. Why did you ever want to do this? Okay, so for the small signal circuit, we're getting rid of that DC source. So V common mode goes away. My VG1 is VID over 2. My VG2 is negative VID over 2. Now this DC source becomes an open circuit. My DC source there becomes an open circuit. And then I have, yeah. Let's see, did I really want to put, do I really need that picture? Okay, and then my gain is going to be looking into the drain of this transistor. What I see is RO4. Looking into the drain of this transistor, I see RO3 in parallel with infinity. So this is still RO3. Looking into the drain of this transistor, what did I see RO1 and RO2. I see RO2 because I'm going to do this as a half circuit because I'm going to ignore the other transistor. RO2 and RO1. Let me look at this. RO3, RO4. I believe that one. I don't believe what I have here for. RO3. Okay. Looking into here. Oh, now if we take this thing and we draw that small signal model. Oh, yeah, this all makes sense. Looking in, sorry.
Does it now?
What? Yeah, you did. You missed the epiphany moment. I suddenly realized why these slides are connected. Looking into this diode, I'm just, okay. Looking into this transistor right here, we're looking into a diode connected transistor, right? So this isn't quite RO3. What I see is I see RO3 in parallel with 1 over GM. These two are in parallel. Okay, so I'm not quite right here. 1 over GM3. But it's not really going to affect the gain of this transistor because we're taking the gain is coming through, we're taking our output off of that one. So the output resistance of side 1 is going to be changed. 1 over GM is much smaller than RO3, but this side's still going to have the same gain. My RO, looking in from the output, this doesn't affect my RO looking in from the output. It's really subtle, and I just never needed to know this before. But Dr. Brower thought it was important. Looking into the output right here, I see RO2 in parallel with RO4. Because that's where the output is. That's what I really care about, which is, in this case, we were given numbers here. Oh, we're not given numbers yet. But that is going to be, and then the gain is going to be GMRO. So that's why we need to put the strap on the side that we don't take V out of, because we would kill our gain if we did that. Because now our gain would be GM, yeah, much smaller. Okay. Now we want to put numbers in here, and yes, my answers turned out to be the same. Yay. My GMRO, RO2 in parallel with RO4, 300K in parallel with 100K. So my RO is 300K in parallel with 100K, which is 75K ohms. And my gain, my differential gain, is GM. Which transistor do I use the GM for? Either M1 or M2. They better be matched, or we've just shot our common rejection ratio. Is 1,000 micro times 75K. And that comes out to be 75 volts per volt. It's positive because it's a differential amp. And whenever I want to calculate the gain in dB, it would be a dB would be 20 log of 75, which is 37.5 dB. Get a much higher gain by putting the active load in there. And you can match it so much better than you can resistors on the board. These are better than 0.01%. There we go. The common mode gain. Now it's going to, okay, so I got a formula for it, thank goodness. It's going to be 1 over GM3. Why does GM3 matter? I don't know. But this is derived in the book, if you want to see that. It's 1 over 2 GM3. And I did convince myself that, oh, because GM3 is the one that's going to influence the resistance. Of course, this is 1 over 2. GM3 is 400 micro. Yes, I got that right. Wow. And RSS is going to be the resistance looking into that transistor right there. This is the current source, is really an NMOS transistor. So it is 300K ohms. Resistance looking into the drain of that would be 300K. And we can calculate a value for that. The common mode gain is whatchamacallit, 0.00417 or minus 47.6 dB. Now, if I wanted to find the common mode rejection ratio, I've got a quick trick here because I've converted these things into dB. Common mode rejection ratio is the differential gain over the common mode gain, magnitude. Okay, my differential mode gain is 37.5 dB. All I have to do is, so this would be deep, when I divide dBs, it's like adding the negative. So I just add their two magnitudes together. 37.5 plus 47.6. This should come out to be roughly like 80 dB. 70, 84,
85.1.
yeah, 85.1 dB.
You take the magnitudes of the.
Yeah, because, okay,
Oh, right, yeah, because the absolute value over absolute value, yeah.
right, because it's AD divided by. So the dB, the logarithm rule would be the divided by becomes addition, but since it's multiplying becomes addition, dividing by becomes subtraction. So I'm subtracting a negative.
Okay. Yeah. I was wondering why you were.
I knew the answer, I just couldn't. I knew you just have to add them together, and it comes out to be about 85 dB. So improving either the differential mode gain or making the common mode gain smaller would help me out. And the way I'd make the common mode gain smaller would be to increase RSS, increase the output resistance of that transistor. I could probably do it fairly easily by doing this on the current source. Make it a little bit, few more transistors. Okay, we're getting there. Yeah, we already calculated that. We found a shortcut. Now, you can have, they call these, they have different flavors of op amps. And one of the ways you improve the performance of an op amp in total is you put an N flavor and a P flavor. This is, the gain transistors are NMOS, so this is an N flavor. N flavor is what people call it. I've never tasted one. 27, okay, so the PMOS version of that is I would have to put the current source, a PMOS current source up at the top would go to VREF. Thank goodness I'm just copying a picture here. because I could never think through this. This would be VG1. I'd have PMOS transistors for gain transistors. They are slower, they have less gain, but they also have less noise than the NMOS transistors. So sometimes there's an advantage to doing this. We got that here. And then I put my strap, wait, I need another transistor here. My active load is going to be N-type. And I put the strap across there. And this gets connected through, because I drew it funny. And I should have drawn it, like flipped it horizontally through here. So this would be the PMOS version of it.
Okay, so it's like the other one, it's just the PMOS are on the bottom and the NMOS on top.
Right. It's kind of, and the current. This is the current source. This is this is the I source. This is the I source here. This these right here are the gain transistors. And these are the gain transistors here. So everything that's PMOS becomes NMOS, and everything that's NMOS becomes PMOS. And this is the active load right here. This is acting as our resistors. Active load. And then this is the active load here. And it gets inverted because the voltages are upside down. Flipping too many polarities in my head at one time, I will make a mistake. So it's just different things in there. The PMOS is a little bit slower. It has a little bit less gain, but it has less noise. And you can help balance it out. Remember that losing the threshold thing? I can help to help get my overall to help get my overall op amp rail to rail. The PMOS version of it is going to be able to pull it closer to VDD. And the NMOS version of it's going to be able to pull it closer to VSS or ground. So if I put the two together, I'm going to have a wider range on my output. And these are little games people play with these little differential pairs, and they turn them into op amps, and they get used all over the place. If I need a comparator inside a memory circuit, I have two choices. I can either put a latch in there, or I can put a diff amp. And I can put a better version of it by putting a P-sense and an N-sense amp in there at the same time. All of this gets used in what we all consider to be digital circuits. What? Okay, we've done this. This is the big picture. What are we doing here? What we want to calculate RN, Rout, and gain. The gain depends upon the slope of this line, and it's going to be much better behaved where the slope looks like a straight line. So in this middle region, we put the Q point here in the middle for best linearity. We put it up here if we want to minimize the current draw. We put it down here if we're crazy. We both want bad linearity and a huge power consumption. Yeah. Small I, good linearity. Bad all around. We're getting close to the end. I'd always just kind of like, it's like a big, this is my least favorite part of this class.
I'm trying to think of any time when you actually want to have high power consumption.
Just for the sake of having high power consumption?
It's too unique.
No.
High
Well,
power consumption also means that you're dealing with like,
if you have a higher power consumption, it's going to go faster. But that isn't necessarily faster.
mm-hmm.
So that doesn't help you there. Sometimes you see, right, yeah. Sometimes you're willing to sacrifice your power efficiency to get performance. But to sacrifice power efficiency to get worse performance is just not cool. So, yeah. Yes. Or you just screwed up. You may not be creating reason. Okay. Yeah. Okay. Gonna look at multi-stage amplifiers again. Learn to recognize what you don't know. I realize every time I go through this that there's more subtle stuff I can learn. It's surprising how much, yeah, you can learn. I was a designer for a long time without understanding a lot of the theory, but okay. This is a two-stage amplifier. I've got this circuit right here is the gold thing is basically just the bias circuit. It's the current reference. I've got an external reference here, could be set by a resistor, and it's setting the current for all the rest of this. So this is also just an I source. And this is also just a current source. When I go through and I want to try to decipher what's going on here, I try to draw a line between the input and the output. In this case, I'm going to start at the positive differential input, and I want to get to the output. So I'm going to have to go through my diff amp gain transistor and through this transistor right here. So Q1 and Q2 are a diff amp. This is easier to decipher than that big ugly op amp. This one right here, my signal input's coming in on the gate. The output's off the drain, so this is a common source. These two transistors right here, Q3 and Q4, I got the diode strap in there. That's my cue that this is the active load. I have put this on the exam before. Can you tell me what all the transistors are doing? And then that is just a current reference right there. And we talked a little bit about the compensation cap. That's to make the Bode plots look pretty. It's to give you a single dominant pole at a lower frequency than the cutoff frequencies and poles and zeros of all these transistors. Okay, we're not going there yet. This is partially exam review. So I've got this transistor here. I got that same circuit here. And I want to, instead of using this model, I want to use this model for it. Because it's a heck of a lot simpler. So I know my stage one is the diff amp. Its input resistance is the input resistance of a common source, looking in there. Rn1 is infinity. The output resistance is RO2 in parallel with RO4. RO1 is RO2 in parallel with RO4. And its gain, GM RO1. I want to do this very conceptually because I want you to get to the ideas here. My stage two is this Q5. We decided this is a common source amplifier. So we can go back to the chart, or we can just remember for a common source amplifier, the input resistance is looking in there. So Rn2 is infinity. And the output resistance, RO2, is R07 in parallel with R06. And the gain, AV2, is going to be, oh wait, let's get this one. AV1 is GM1 or 2. The gain of this one is going to be GM6 because it's Q6 transistor times RO2. So if we wanted to figure out how this works together as a two-stage amplifier, my RN on stage 1 was infinity. That's just an open circuit. My gain is whatever number I got for AV1 times that voltage there. My output resistance is RO1. We could get a number for that. My input resistance to the next stage is infinity. The gain of this one is AV2. And the output resistance there is, whatchamacallit, it is RO2. Given these numbers right here, we could do calculations for all of those, fairly simply. But if you can map from this down to this model, you're doing pretty good. And yeah, I've been putting that on the exam in here for like 2 or 3 years. Maybe I'd give you those values and I just tell you to put it into a 2 or 3 stage model of an amplifier. But that's really the big picture that everyone needs to know out of this, not just the IC designers, is being able to look at a circuit or an op-amp, figure out its output resistance. Can it drive the load that I want it to? It's like the most common problem I've seen anywhere with students and with young engineers. They don't think about the output resistance. So we want to figure out what is the overall RN, RO, and AV0. So let's go through here and put some numbers on here. I'm gonna do the, I don't have enough time to do that. I have enough time to do this though. So the numbers I've got here are my RO1 is 75K. My AV1 is 30. So this is 30 times VN. My RN here is infinity. We've already got that out. And my RO2 is 75K also. And my gain on this stage is negative 75. Now I put a load resistor on here. This is the important part. I put my load resistor on here is 100K ohms, and my signal resistance is 300 ohms. So my load, what did I say? 100K and 300. So my load resistance would go right here. Our load is 300K, and my signal resistance would go right here, and that was 300 ohms. This was 100K. This is 300 ohms. And this is my signal input, VN. Can I go through that circuit, calculate the voltage dividers, and figure out what's going on? The input and the output resistance is pretty straightforward. The input resistance is the resistance looking in here overall. So for my 2-stage, my RN would be infinity because it's the input resistance looking into the first stage. My output resistance would be the resistance looking into here, and it's the output resistance of the second stage. And the gain is going to be a little bit trickier In this case, because this is infinity, this will be Vn. And this would be 30 Vn. And this also has infinity, so it's just 30 times 75. That doesn't always work. If the input resistance isn't infinite, that doesn't work. You have to actually calculate the voltage dividers. 30 times negative 75. And you could replace this whole big mess with a single one-stage equivalent. That's probably the most important skill you can get out of this class, I think, exam problem. And that's what we did here. Yeah, you got to practice this stuff. This is Dr. Brower's exam review. I would highly recommend looking at this when you're studying from the exam, because a lot of the circuits that I use, I just pulled off of Dr. Brower's old exams and regurgitate them and change them around a bit. And I got like a pool of about 30 problems here. When I write an exam, I just start pulling things out of that pool. So, what?
Just imagine throwing darts at problems and you're just like, that's going on.
It's not really random. They fall into like certain categories. There's 5 or 6 of one category and 5 or 6 of another. And I kind of like pick one from every category. And then I find something that's really like taking me off that semester that I really want to see people learn. And then I may put like 2 in there for that one. Yeah, lately the input resistance, output resistance, and gain is like my personal tirade against microchip. So this is an example of a circuit. If you could figure out the input resistance of stage 1 and the output resistance and the gain of stage 1, input resistance, output resistance of stage 2, you could plug it into this model and you could figure out the overall gain of this. And we just did an example like this. I'm going to fly through these. Yeah, and we could turn it into another model. This is a bad amplifier. Why is it a bad amplifier? It's a bad amplifier because it has a high output resistance right there on stage 2. And you could fix that. You can identify the problems. So this model of the amplifier is really important. This chart will help you out if there's a common source of source resistance, common gate, common drain. I tend to put more of these in there and less of those because these you can kind of like, you know, you can figure out. They're easier to figure out. Diff amps and cascodes. You're more likely to see more of the red stuff than you are the common gate and the common drain. Maybe as an output stage or something like that. Be able to identify these circuits, know this chart and how to apply it. What is the resistance looking into each of those 3 terminals of the device? Finding REQ. Yes, this problem has shown up on exams before. Can you find all the REQs? And if not, there's at least one problem on there that's finding the REQs. Can you draw the DC and AC equivalent circuits? You know the rules how to do that. I'm not putting that on the exam. This is a homework problem, but there may be ideas from that on the exam. This is a diff amp. These are, yeah, there's a lot of, these are Dr. Brower's exam problem circuits right here. I use some of her problems. So, I mean, it's a good reference. And then I'm done. I also draw my own circuits sometimes too. But sometimes I make you draw the circuits. And yeah, it's not as terrible as it could be. It's not like you're taking the final in here.
But overall, it's kind of the same on the street circuit, it's just gonna be different.
Right. It's if you okay, so there's a couple things you have to do. You may have to calculate the DC bias point. I'm going to give you enough information to calculate that. Okay, you may have to calculate GM and RO. You may have to do some stuff that could have shown up on exam 1. So you bring in your exam 1 note sheet. Let's see, DC bias point, GM and RO, drawing the AC and DC circuits, and figuring out the input resistance, output resistance, and gain of the circuit that you're given. And that 2-stage, 3-stage model of the amplifier. That's a big deal. Okay. So stuff to review. I'll be in my office. I won't be in my office tomorrow. I'm going to go home and work on your exam. I'm going to go hiking and then I'm going to work on your exam.
Just gonna hold office hours next week?
I will have office hours next week. And my secret office hours are on Mondays. I usually get in about 10 and I don't have a class until 4. I'm usually just in there loading stuff into BB Learn. So you can bug me anytime there. I'll answer emails, or you can come in, or you can, if you actually come into my Zoom, I get an email, and I know you're there. So either way, yeah.
Okay.
Okay. So yeah, start studying, because this is harder than exam 1, and which is the final exam is actually harder than exam 2. But the bonus is if you do well on the lab, which labs are a lot of work in here, you do well in the labs, you do well on the homework, you do well on the exams, then there's a cutoff point somewhere in there, and you're exempt from the final. It's usually the what? Yeah. And it varies from semester to semester, but it's usually, there's only 15 people in here, so probably about 3 or 4 of you. Depending, you know, yeah, it just depends. I may be generous this semester, because again, I think that you guys are going above and beyond the call of duty, putting up with all the weird stuff in the world on top of coming to school and trying to stay active in the world. Okay, so Amelia, you're not here. Alex, oh, she had a job interview. That's right. So she can watch it on video. And Alex, okay, and everybody else is here. Okay, I will see you guys. It's time to go. Yes. Tell her to watch the video, because I told you what on the exam.
I will. I'm sure she will.
What? Yes, she will.